Imagine you have this polynomial of degree n, and then we need to apply the basic definition of big omega on f of x. Like big O, we will have two methods. The first will be ad hoc calculations, and the second using a general procedure. Now for the ad hoc calculations, the steps will be a little bit different than big O. Let me show you by an example. Suppose we have a function f of x is equal to 3x squared plus 7x plus 2. And now we need to find a function to prove that f of x belongs to big O of this function, which we will call it g of x. Now, according to the basic definition for big omega, we need to find 3x squared plus 7x plus 2 greater than or equal to a constant multiplied by g of x for all x greater than a value of k. Now, remember that for big omega, g of x will be like a lower bound. So any function that you can draw below this function will be a candidate for g of x. So any polynomial of degree less than 2 can be a value for g of x. So you can put for g of x as an example, you can put 3x plus 2, you can put x raised to power half, and etc. But the best one that is close to this polynomial is that you choose g of x as the dominant term. So the best answer for this is to choose the value of g of x as x squared. So what you need to prove now, you need to prove that 3x squared plus 7x plus 2 greater than or equal to a constant multiplied by x squared. Now, if all the coefficients of this polynomial are positive, then it is very easy to find this constant. So, if you want to make the left-hand side larger than the right-hand side, just simply ignore all other terms other than the dominant term. So, we can say that 3x squared plus 7x plus 2 greater than or equal to only 3x squared, and this can be true for x greater than or equal to 1. So simply ignore all the other terms other than the dominant term, and you will get to your answer. So here you have the value of c is equal to 3. As a result, we can say that if you have a polynomial such that all the coefficients are positive, then you can choose g of x as the power of x of the dominant term. However, if you have a polynomial that has some of its coefficients negative, for example, if you have 4x raised to power 5 minus 3x raised to power 4 plus 2x raised to power 3 minus 7x squared minus 7. So how to find a value of a constant c to make this left-hand side equation is greater than or equal to c multiplied by g of x. Again, for g of x, you need to choose a function that is close to this polynomial, so will be x raised to power 5. So it's not like before that you can ignore some of the coefficients. You can ignore the positive part, but you cannot ignore the negative terms. Why? Because usually if you have minus, then you are reducing the value of the function, and it's difficult to make it greater than or equal to a constant multiplied by x raised to power 5. So we need a trick here to show that the left-hand side is greater than or equal to a constant multiplied by x raised to power 5. So how to find this constant to make the left-hand side greater than or equal to right-hand side? So let us consider a polynomial that has some negative coefficients. Now we need to find big omega, which is a lower bound of this polynomial, which is a 3x raised to power 4 minus 90x raised to power 3 plus 3. Let me show you the trick how you can prove that this polynomial can be written as greater than or equal to a constant multiplied by x raised to power 4. To find big O of this polynomial, we need to write the objective. So what is the objective? Our objective is to prove that the polynomial 3x raised to power 4 minus 90x raised to power 3 plus 3 is greater than or equal to a constant multiplied by a power of x of the dominant term, which is this term. So the power x of this dominant term is x raised to power 4. We will break the ad hoc calculations into steps. The first step is to remove all terms of the polynomial with positive coefficients. So look at the polynomial. We have two terms with positive coefficients. This is the first one and this is the second one, but this is the dominant term. So we should not remove it from the polynomial, otherwise the degree of the polynomial will change. So there is only one term with positive coefficient, which is this one. So when you remove positive coefficients, then the value of the polynomial will be reduced. So as a result, we say that for x greater than 1, the polynomial 3x raised to power 4 minus 90x raised to power 3 plus 3. When you remove 3, then the resulted polynomial will be less than the original polynomial. So we write greater than or equal to 3x raised to power 4 minus 90x raised to power 3, which is the remaining parts of the polynomial when all terms with positive coefficients are removed. In the next step, we are going to split the dominant term, which is 3x raised to power 4, into two parts, 2x raised to power 4 plus x raised to power 4. So we have 3x raised to power 4 minus 90x raised to power 3 is equal to 2x raised to power 4 plus x raised to power 4 minus 90x raised to power 3. Now we will look at this polynomial. We will consider the following. If x raised to power 4 minus 90x raised to power 3 is positive, look at this part, okay? If this part, so I will put brackets, maybe I will cloud it now. So we will cloud it here. So if this part is positive, then what we will conclude? We will conclude that 2x raised to power 4 plus, I will put a bracket, x raised to power 4 minus 90x raised to power 3 will be greater than or equal to this part, which is 2x raised to power 4. Let us look now closely again to this relationship. And again, I will cloud also this part. Now, if this part is greater than or equal to 0, if this is positive, then definitely when you add it to this term, it will be greater than to 2x raised to power 4. So to find the range of x that makes this part of the polynomial greater than or equal to 0, then we need to solve this equation as an inequality. So we can say the following. What is the value of x that makes x raised to power 4 minus 90x raised to power 3 is greater than or equal to 0? We will solve this inequality, and you have learned in calculus how to solve an inequality finding a range of x. Take x raised to power 3 common, so you will have x minus 90 greater than or equal to 0. So the solution is either x less than or to 0, or I will just leave a space, or x greater than or equal to 90. How? If x is negative, then this part will be negative and this part will be negative. The multiplication of negative with negative will be positive. And if this part is true, so x is greater or equal to 90, so this part is positive, and also this part will be positive, so a positive multiplied by positive will be greater than or equal to 0. But this one is rejected. Why it is rejected? Because we will consider only x that are greater than or equal to 1, and it's greater than or equal to 90. So we can say that now for x greater than or equal to 90, we will have the following. We will have 2x raised to power 4 plus x raised to power 4 minus 90x raised to power 3 greater than or equal to 2x raised to power 4. Now by the last statement, we have reached our conclusion that the polynomial is greater than or equal to a constant multiplied by the power of x of the dominant term. The ad hoc calculations for this example are also summarized here. So the polynomial was rewritten such that the dominant term was splitted into two parts and all terms with positive coefficients were removed. Also, we proved that for x greater than or equal to 90, this part of the polynomial was always positive. So therefore, 3x raised to power 4 minus 90x raised to power 3 plus 3 is always greater than or equal to 2x raised to power 4. Therefore, g of x will be x raised to power 4, k is 90, and c is equal to 2 as witnesses. Now to find big omega of a polynomial using a general procedure, here are the steps. First step, you assume that g of x will be the power of x of the dominant term. Second step depends on the coefficients of the polynomial. If all coefficients are non-negative, it means positive, then you assume k is equal to 1 and c will be equal to the coefficient of the dominant term as witnesses. But if some of the coefficients are negative, like for example, this example, then you need to find you need to find a value of d, and the value of d is equal to, you add all the absolute values of the coefficients of all terms except the dominant term. You divide it by the coefficient of the dominant term and you multiply the result by 2. You call this value d. Then for finding k, find the maximum between 1 and the value of d you have obtained from this equation. And for c, you divide the coefficient of the dominant term by 2. Let us apply it on an example. Imagine you have the following polynomial and we need to use the general procedure to find big omega of this polynomial. Then notice we have some negative coefficients here, so we cannot apply this rule. So we have to apply the second rule. First we need to find d. So what is d? Add all the coefficients, the absolute value of the coefficients of all terms except the dominant term. So you add, this is the coefficient for the dominant term, so you add 6 plus 4 plus 4 plus 7. Then you divide the result by the coefficient of the dominant term, which is 3. And then you multiply by 2. So here we are multiplying 2 over the coefficient of the dominant term, which is 3, by the summation of the absolute values of all coefficients other than the coefficient of the dominant term. The result is equal to 2 over 3 multiplied by 21. So in this case, g of x will be the power of x of the dominant term, which is n raised to power 6, and c will be equal to the coefficient of the dominant term 3 divided by 2, and k will be the maximum between d and 1, and the maximum is equal to 2 over 3 multiplied by 21. By this example, we have completed our lecture for today. Good luck and see you in the next lecture.